specificity changed. And I'm just using one sample. I'm just showing a representative sample from each of those time points. Now, what should strike you is that at week 5, we saw a great diversity in recognition compared to week 0 and 2, which only recognized about 2 proteins, 4 if you're stretching it. Week 5, which is where we saw that rapid increase in titer, we see maybe 11 bands, maybe more being recognized. And that progression continued until about week 14. And from there, the recognition stabilized. Unlike titer, recognition didn't drop. Now, how did the cross-linking change throughout the immune response? When we look at total antibody, what you should see is that there's actually very little variability. This represents the tetramer, trimer, dimer, monomer. And just focus on the tetramer here. It remains highly consistent from week to week. That is, it remains about at 43% of all antibody. We did have an exception, and that was week 2, where it actually contracted a little bit. And we found that the significant difference in all these samples was due to this single week. Now, what we can attribute this to, we don't know. It could be the adjuvant that we use in vaccines. We're not sure. Now, this is where things get exciting. Look at how different the specific antibody profile is. Overall, you see a change in the degree of cross-linking to go from low cross-linking, where you have that flexible antibody, to high cross-linking, where it becomes fully bound and rigid. So focus on weeks 0 and 2. What makes up the majority of antibody is the trimer. Actually, week 2, it makes up about 50% of all antibody. And the tetramer here is actually less in proportion than the monomer. Week 5, where we saw that increase in titer and specificity, we see that the tetramer makes up about 50% of all specific antibody. Now, this progression remains, the degree of cross-linking was rated, what am I trying to say here? The tetramer represented about 40% of all antibody, 43% throughout all weeks. And it only began to contract at about week 37. And it returned to the populational average of the total antibody. It was about 43% there. And what you should also notice is that the error bars within each week are very small. That is, the samples were consistent from fish to fish within a week. Now, to make this easier to digest, what we did was determine the ratio of the specific tetramer to total tetramer. Now, if the fish were just letting their antibody bind randomly, if they didn't regulate the degree of cross-linking, we'd expect a 1-to-1 ratio throughout all of these weeks. But what you can see is that that's not the case. Week 0 and 2, as you would expect, it was actually below 1, meaning the specific tetramer was less than the total tetramer, the proportions. Week 5, it went above 1, and that continued throughout 21 weeks. The only exception was week 8. And again, I can't really explain that. There was a lot of variability in that one group, where some did have mostly tetramer, some had mostly trimer. And as I said, week 37, which isn't shown here, it returned to 1. And we believe that's a return to homeostasis, but we don't really know, because we don't have time points that are before that week, from 21 to 37, and we don't have time points afterwards. Now, this led us to wonder if there was actually a change in the affinity. Cross-linking was actually correlated with affinity. So we checked how affinity changed throughout the immune response. And each of these points here represents one fish. And what we did was track the average from that time point. And what you can see is that at 21 weeks post-immunization, the affinity increased nearly tenfold from control. And that doesn't sound like a huge increase in affinity, but remember what I said. Small increases in affinity can lead into large changes in the sum of affinity, known as avidity. We then wanted to determine, hey, are the degree of cross-linking and affinity correlated? So we did just that. We plotted them together. And again, each of these points represents a single serum sample. And what you can see is that when the tetramer is low in abundance, the affinity tends to be low. When it's high in abundance, that is, makes up maybe like 50% of all antibody, the affinity tends to be high. And at this point, I'm just saying that there's a correlation between the two. I'm not trying to say that there's a causation. Now, what's interesting is I didn't see this level of correlation when I plotted the titer and affinity together. That is, a fish could, secrete high amounts of low affinity antibody, could secrete moderate amounts of high affinity antibody. And this could represent a trade-off for the fish. So just to summarize the results, it was a lot to digest, but we saw an increase in quantity, an increase in the specificity, an increase in quality, which was represented by the degree of cross-linking, and another increase in quality, which was an increase in the affinity. So on to my discussion. So what's exciting is that for the first time, IgM has been shown to be a dynamic molecule in both affinity and degree of cross-linking to an actual pathogen, not just a simple defined antigen. But so what? What does that matter? So just to begin with that question, our fish had a disadvantage in comparison to mammals. So there's an estimated 10 to the 29 prokaryotic cells per mil of water in the ocean. Now I'm not saying... Alright, so let's look at the different effector functions versus the mammalian isotypes, IgM, IgG, IgA, IgE. Each plus sign here represents how well that particular antibody can carry out a certain effector function. A negative sign means it can't carry out that effector function. So IgM, for example, is great at complement activation in mammals. It's okay at neutralization, can't do mast cell binding at all. Just to make this a little more simple to understand, let's go back to that original figure. IgA, great at neutralization, IgG, great at opsonization, IgM, great at complement. They each specialize for a certain effector function. Now, maybe fish actually do have their own isotypes, but rather than different classes of antibody, they change their cross-linking. So this highly cross-linked rigid form could be the equivalent of IgM, for example, great at complement. This low cross-linked form, maybe that's equivalent to IgE in mammals. But I believe that it goes beyond that. That theory I proposed where there are different effector functions was proposed by Qatari in the early 90s. And I have my own theory that flexibility is related to the degree of recognition of IgM. And I'll get to what I mean by that, but let's just start with the classical clonal theory. According to the classical clonal theory, the antibody binds to the antigen like a lock and key, like I said before. And it tends to view the antibody as two discrete units. The Fab fragment, which binds the antibody, and the tail region, the Fc, which carries out the effector functions. They're discrete units. And the antibody binds the antigen like a lock and key. That is, if it doesn't fit, you must quit. In contrast, the instructive hypothesis, which was proposed by Linus Pauling in the 1940s, sees the antibody as far more flexible. Sees the antibody as plastic. It's able to mold to different antigens. It doesn't act as a lock and key. So that's not binding like a lock and key. Now, the newest hypotheses that are coming out don't favor either of those hypotheses. Instead, what they're saying is we need to combine both of those theories into one. So rather than taking these as discrete units, the Fab and Fc, they've been taking a holistic standpoint to the antibody, where this tail region can actually affect the head region, the binding. So as I said, they take a holistic approach. Now what you're probably wondering, is this actually demonstrated in mammals? And the case is yes. So what I have here is Cryptococcus. Cryptococcus is a fungus. And what the researchers did was they took antibody that had all the same binding regions. Where they differed were those tail regions that, according to the classical theory, shouldn't affect binding. And each of these antibodies was labeled with a fluorescent tag. What you can see is recognition here with one antibody is kind of a halo effect. Here it's fully lit up. So thus there is differences in binding. And this is where I believe it relates to fish. Regions away from the binding site, those disulfide bonds, can actually affect binding. So to put this in perspective, let's start at the beginning of the immune response, week 0 and 2, where I just introduced my antigen to the fish. I just vaccinated them. Few B cells are actually going to bind to my antigen. There's going to be little competition, so all B cells will bind. Those that bind with low affinity, and those that bind with high affinity, which are going to be few in number. Where they're going to differ, however, is in the signal that they get from that binding. These that bind with low affinity, I believe, are going to receive a weak signal. This has actually been demonstrated in literature. Those that bind with high affinity get a high signal. And this is going to result in the multiplication of the B cells, but what they're going to differ in is the antibody that they produce. Those that received a weak signal are going to produce a significant amount of low cross-linked antibody. Those that receive the strong signal produce low amounts of highly cross-linked antibody. Now, where these antibodies differ is in what they can recognize. Now, as I said, low cross-linked antibody has high flexibility. So it's going to bind with low specificity and can bind many antigens, but it's going to do so with low affinity. Those that have high cross-link, that are highly rigid, act like a lock and key. So they bind only one antigen, but they're going to do so with high affinity. And this is exactly what I saw at the beginning of the response, where you had low cross-linked antibody predominating. We had low titers because few B cells were being activated, and also the affinity was low. But now let's see what happens when the immune response progresses. Antibodies are clearing the antigen that I introduced, and thus there's going to be a competition for the little antigen that's present. So what do you think is going to win? Well, obviously, those cells that combine with the highest affinity. So predominantly, low affinity antibodies are going to die out because they're not being activated. The high affinity antibodies, on the other hand, are being activated and they're going to multiply. Now, as I said before, that affects cross-linking, that signal that they got. But in this case, the highly cross-linked antibody is going to predominate versus the low cross-linked. And this is exactly what we saw from weeks 5 to 37, where we saw these cross-linking increase throughout the immune response. Also, we saw titers increase, and we saw affinity increase. So, putting this all together, why would a fish want to have low cross-linked antibody at all? Well, what I believe is that flexible antibodies allow a fish to recognize pathogens it may have never seen in its lifetime, so it doesn't have any memory for them. And also, it can adjust to pathogens that are in an arms race with it, that is, to evolve, to win out. Also, these flexible antibodies likely act as natural antibodies, and we too have natural antibodies. Now, natural antibodies are unlikely to actually be effective at combating a pathogen, but what they can do is delay infection until we mount a robust immune response. And the robust immune response in my study occurred around week 5. And that's where we saw the increase in titers, increase in cross-linking, the increase in specificity, increase in affinity. And as I said, cross-linking could be an alternative to the mammalian isotypes. So fully cross-linked could be equivalent of IgM, great at complement. No cross-linking could be the equivalent of IgE. So where do I see this work going? Well, first I want to know if there's actually evidence